Okay, thank you for this introduction. Good evening, everybody. I hope you are having a good time in Santa Barbara. Here it's not so fun to be to have this time shift and to be alone and to be in the cold while you are all together and enjoying, I guess, better weather. So I will talk about chemical mixing in stars. And actually, I decided to take a different angle of view of the other talks we had during the week, and I will actually try to gather different constraints that come from different surveys, and also the implications that chemical mixing might have in the reading of these surveys. So just to start, a little bit of terminology. What we usually call classical models are the models that include no transport process beyond convection. And what is called standard models are the models which actually include also atomic diffusion. And the non-standard models are all the rest. So when you include any kind of process, of transport process, you can imagine. So before discussing the chemical mixing, the first question to ask is, why do we care actually as stellar physicists? You all know that the transport processes of chemicals modify the chemical stratification within the stars, hence that modifies the opacity and the thermal structure of the stars within the stars. That also changes the amount of fuel which is available for burning at the different phases. And that also changes the properties of the stellar atmosphere. And here you have a nice graphic that actually shows the abundances within the star, so with the center here and the surface here for 2.5 solar mass star, where atomic diffusion and turbulence are included. In a classical model, you wouldn't see any variation in the outside of the star. You would only see variations due to nuclear burning. And here you see that actually the abundances have changed at the surface within the external part of the star due to these processes. So due to this new chemical stratification, the internal structure is going to change. The pressure, temperature, density within the star is going to change compared to a classical model. And of course, the asteroseismic properties will also change. As a consequence, all the outputs of the stellar models, all the stellar parameters, the classical one, the luminosity, effective temperature, radius, the lifetimes at the different stages are going to change. Also, the evolution paths are going to change. You can see here, for example, the variations of the paths in the HR diagram of a 3 solar mass star. When you include the rotation or overshooting, I will come back to these differences in a moment. And you see that due to these transport processes, the luminosity, the effective temperature, and the radius of the star change. That has consequences on the spectral energy distribution, which is important in some cases, and also on the variability of the stars. This has implications also on the size of the core, hence on the type of remnants, black hole versus neutron stars, the composition of the remnants, their rotation also, as we will see in a moment. And of course, that has some consequences on the yields. So the nucleosynthesis is going to change when you have transport processes, and also the wind of the stars, the radiation they emit, and the energies they inject in the interstellar medium is going to change due to these processes. So all the outputs of the stellar models are going to change due to these processes. So this is why we care as a stellar physicists, but we also have to worry about why other astrophysicists care, people working on different topics. Of course, because of these changes, the ages we are going to determine for the stars, the variation of the initial composition versus the present chemical composition of the stars that we observe, the isochrones that we are going to produce are going to change. And this has a huge number of consequences. I quote only a few here. it's very important when you make stellar population studies, when you want to do some chemical tagging, age dating, when you want to derive the age metallicity relation, and at the end, when you want to do precise galactic archaeology and try to understand how the different substructures of the galaxy formed, how they were accreted, etc. This has also some impact on the fact that the stellar masses that we are going to determine, the radii and the internal structure that we are going to predict, will have some consequences on the predictions for the formation and the dynamics of multiple star systems and also of planetary systems, with some consequences, for example, in the characterization of exoplanets and exoplanetary systems, and eventually on the habitability of these systems. The fact that we change the stellar remnants has some implication to understand the stellar explosions, the formation of black holes versus the formation of neutron stars, which has some implication for to interpret the gravitational wave events. And also this has other implications. For example, when you want to study the long-term dynamical evolution of star clusters, the remnant you produce has some implication for their dynamical evolution and also for their contribution to the field populations. The nucleosynthesis changes, as I said, the winds, etc. So this has some consequences when we want to interpret or when we want to explain the astrophysical periodic table, when we want to understand what were the first stars in the universe, the so-called pop-tree stars, and when we want to do galactic chemical evolution. Also, when we want to understand the feedback of stars on the interstellar matter, which is very important for star formation, and also when we, for example, have some populations which are not resolved in external galaxies. This has very important consequences on these studies. And also now there are some cosmological simulations which take into account the feedback of stars, and this is also very important for these purposes. And last but not least, and we could actually find other examples, that will change the variability of the star, and it's very important when you want to use extragalactic distance scales through Cepheids, for example. So this is why this symposium or this workshop is very important, because we are here to discuss all these aspects, and we all know that the stars are actually very complex, and the complexity is to go from these 3D magneto-hydrodynamic objects to some very simple 1D models. And the challenge is actually that there is a large scale in both in space and in time that we have to cope with in order to explain the different processes going, which are at work within the stars. So recently, over the years, there have been lots of 2D, 3D numerical simulations and also laboratory experiments which start to make some quite good predictions for these multi-dimensional processes. But as you discussed previously during this workshop, this is going from the 3D to the 1D is not trivial. The simulations don't run in the stellar regime, so you need to rescale to match the stellar conditions. There are also the challenge of the interactions between the different processes, which make which increase the difficulty. So I mentioned that we are in the area of large surveys. We might be able to have new constraints. And actually, the stellar astrophysics is revolutionized by these large-scale surveys. The first one, of course, comes from Gaia, which gives precise distances, proper motions of stars in the galaxy. Spectroscopy, which is very often affiliated to Gaia, so the Gaia ISO survey, GALA, etc., all these surveys that provide stellar parameters, abundances, etc., for 100,000 stars in a consistent way are very, very important. Asteroseismology also precises some important clues on the internal properties of the star, the internal rotation, but also the mass, etc. And spectropolarimetry, which I won't touch much in this talk, is also important to have clues on magnetic field and rotation in stars of different types. So talking about mixing processes is a big task, and fortunately there have already been lots of talks during this week and also the weeks before, talking about different aspects. Convection we heard before, and magnetic instabilities are going to come. Also internal gravity waves are going to come. So I'm going to focus today on three processes, which are microscopic diffusion, rotation-induced mixing, and thermal-in mixing. So let's start with microscopic diffusion, which has been studied for a long time now, which has been studied by many people, both for the formalism and also for the applications. And it's well known that this process is relatively important and efficient already in the Sun and solar type stars, but also in warmer main sequence stars. Also, it's important to interpret the observations of horizontal branch stars and also of the hottest white dwarfs. So what is microscopic diffusion? It comes naturally from the gaseous nature of stars, and it is split in different processes. Some of them are due to the collisions among gas particles due to stratification, so either density and pressure gradients or thermal and chemical gradients. And in principle, these characteristics can be derived from first principles. But it's still a challenging task because we have to take into account non-classical interactions between the particles, and we are using a formalism that was initiated by Burgers, which has some limitation. On the other hand, another process which is important is due to the momentum transfer from the photons to the gas particles, which is radiative acceleration, which is actually acting differentially on different non-fully ionized species. This is also quite difficult to treat in the models. This requires detailed knowledge of the ionization levels for all the chemical species. And this requires, in principle, the use of monochromatic opacity instead of Rosland opacity. And I think there is only one code where this is treated properly, which is the Montreal and Montpellier code, where all these things are taken into account. In other codes, we use parametric approximations, what is called the SVP approximation, which actually separates the terms that depend on the atomic data from those that depend on the concentration of the individual species. So here in this figure, you can see the predictions of the abundances in the photosphere of a low mass star. So I took this low mass star just on purpose, because usually we say it's in stars more massive than the Sun. But actually, this star is a low metallicity star. Hence, it has an effective temperature which is higher than that of the Sun. And this is why you can see the effect, for example, here of atomic diffusion and radiative levitation for some of the elements. On the other hand, here you can see the variation of the abundances when there is no radiative levitation taken into account. And you see that the differences come mainly from the mass of the different atoms. So when you see this kind of variation, abundance variations actually in the models, and you try to confront with observations, actually it's well known that very rarely stars actually show such overabundance of these elements, for example here. And this was already discussed by Eddington in 1929, who suggested that there should be some transport processes that should counteract this atomic diffusion, and he related that to the internal circulation in rotating stars. There have been other suggestions. So rotation-induced mixing is one of the favorite process to counterbalance the effect of atomic diffusion. But mass loss has been invoked, also thermal-in mixing induced by radiative levitation itself, and in general, in the models, actually, what people use are the so-called ad hoc or generic turbulence to counterbalance these effects. And here in blue and green, you can see the variations which are obtained when you actually include a parametric turbulent mixing, which is here temperature dependent, which actually acts in the external layers and which flattens this curve. Here you have a nice collection of plots that shows the predicted variations of different elements from iron to calcium for stars of different ages and for this metallicity. And the first thing you see, as previously, is that the photospheric signatures that are predicted in a model depend on the species. It also depends on the effective temperature. The hotter the star, the more efficient is the atomic diffusion. And this is simply related to the fact that when you move to higher effective temperature, the depth of the convective envelope of the star is much thinner. And actually the time scale for atomic diffusion decreases with decreasing density. So this is why you have this increase of the efficiency of atomic diffusion at the turnoff, for example. The other thing you see is that that also depends on the evolution phase. So this is more efficient at the turnoff. And you see that for the red giant stars, there is actually no more variation. It's simply due to the first redship, which when the convective envelope engulfs the regions where atomic diffusion has actually accumulated the elements. So when people do some chemical tagging, they should absolutely consider stars at the same evolution phases. And this can be seen, so these were model predictions, and here you have some observations, for example, in M67, where you see the variation, the color code gives you the variation in Fe over H. These are very subtle variations, but nevertheless, they can be determined. And you see that the most extreme variations are at the turnoff, and when you move to the red giant branch, the stars have more or less all the same composition. This is seen also in globular clusters. So here is NGC 6397. So you have stars at the turnoff, which are here, and then you have stars along the red giant, the subgiant branch, and then the red giant branch. And you see again that there is this effect of stronger atomic diffusion at the turnoff, and then the effect of the dredge-up. And this kind of data is actually used to parameterize this density-dependent turbulent mixing. This can be calibrated on the globular clusters. And it has been shown by Suzanne Talon and collaborators that this, the actual value of this mixing, or its actual amplitude, is very similar to what you expect with rotation-induced processes. So it's important because even if you don't see if there is some turbulence that counteracts the effect outside the star or in the external part of the star, atomic diffusion still plays a role inside, and this changes the lifetime of the star. And here you can see, for example, the fact of when you include atomic diffusion, the isochrones move to the right. That means that you are going to determine ages which are reduced compared to isochrones, these ones, which are computed without atomic diffusion. So these are for tracks for non-diffusion and pure atomic diffusion. And here you have tracks that are for the models that I showed before with different turbulence. And you see that actually this turbulence, when you have only atomic diffusion, you shift to the red here, and when you have turbulence, you move again slightly to the blue. So the truth is between these two extremes, and this leads to a reduction of about 12% at the turnoff in the age at the turnoff, and this was a way to reconcile actually the age of the universe to the age of the globular clusters. So it's very important to determine the age of star clusters. It's very important, as I said before, for chemical tagging. Here you have a difference in ages when you take into account variable atomic diffusion versus no atomic diffusion. You see that the age differences can be very important, up to 20% for the galactic disk population. And this has an effect when you want to derive the age metallicity relation. So the takeaway message for microscopic diffusion is that it occurs in all stars on time scale which depend on the star and which also depend on the competition with macroscopic processes. In principle, it's beautiful physics that we are actually mixing with this ugly parametrization that I showed before. So now rotation. Rotation has been studied for a long time. I mentioned the suggestion of Eddington about rotation counteracting the effect of atomic diffusion. And there has been the equation for rotating stars have been already derived in the 20s. And in the 60s, rotation was considered only as a second order effect. But since the 80s, there is a lot of observations that have shown that the role of rotation is very important. And here I have listed a couple of work focusing on rotation, but there are, of course, many more in the literature. I think we can say now that stellar evolution is actually not only a function of mass and metallicity, but also on rotation. So before discussing the mixing, I would like to emphasize a couple of additional effects that people overlook sometimes. So when you have strong rotation, actually the centrifugal effects are going to deform the surface of the star. And this is something that we observe. So here you have a real star, which is a B-type star, which is really oblate. And it's actually a very fast rotator. And this is due to this deformation through the centrifugal effects which are reproduced here for where you see the radius, so the polar radius and the equatorial radius for different value of the angular velocity with respect to the critical velocity, which is defined here. And this is very important because this modifies the effective gravity along the star, and this modifies the effective temperature and the flux of the star. And this, if you consider stars actually which are either seen equatorial on the equator or on the pole, you see that you can interpret, you get very different effective temperature, and you can make strong errors on the age and the mass determination that of your star. It's also very important because it drives anisotropic mass loss. It has an effect on the radiatively driven mass loss in massive stars, but it can also lead to a mechanical mass loss at the equator, which can be very important at very high rotation. What is a classical scheme for rotation then? So as we saw, there is a modification of the mechanical equilibrium, which leads to some structural changes. And due to this modification and also to external torques, either in principle by magnetized winds or by tidal effects with a companion, this drives meridional circulation, which itself leads to differential rotation, which leads to different instabilities. And one of them, which is on which people focus more, is a shear instability. I will come back to that also in a moment. This has a retroaction effect on the meridional circulation itself, which increases the modification of the mechanical equilibrium. And all this leads to the transport of both chemicals and angular momentum. And you have this loop, which is going on, that changes again the chemicals and the structure of the star, and that has an effect on the mechanical equilibrium, and you have this loop going on. And as I mentioned before, also the mass loss is going to be modified. So this is what we call the classical scheme. And there has been different ways of treating that, and the Zahn and collaborators way makes the following assumption. This is the treatment that I'm going to discuss now. I'm going to show you some models where this treatment is accounted for in different codes. And the key assumption here is that the anisotropic turbulent transport is stronger in the horizontal direction than in the vertical one because of the stratification within the star. So this is a scheme that shows you that, where you have this vertical and horizontal turbulence, which is highly anisotropic. This leads to the fact that we can assume that the angular velocity is constant on isobars, as shown in this graph by Matteo, meaning that any quantity can be expressed as a function of pressure only. So I won't spend too much time on these equations, but actually when you consider rotation in your models, you have to modify the stellar structure equations to write them on isobars instead of equipotentials. Now, if we focus on the transport of chemicals and angular momentum, so both are totally connected, as you saw in this global scheme. You cannot treat rotation-induced mixing without treating the transport of angular momentum. So in the Zahn and Meder formulation, we consider advection. A meridional circulation is treated as an advection. And this is included in different codes, Genex, Tarevol, Sestam, Franek, while in other codes, this meridional circulation is treated as a diffusion a la Endal and Sofia, and this is the case for these codes. Then you have also the transport of angular momentum through the shear instability, which is here, and eventually through magnetic instability. So both come into this part of the equation. And if you have other processes that play a role, like internal gravity waves, you have this luminosity, which has to be taken into account to modify the angular momentum at different layers within the star. And of course, you have to consider the extraction, the stellar wind, the angular momentum extraction through the stellar wind as a surface condition. Now, for the transport of chemicals, the expression is much simpler. So here you have for a given isotope, you have the variations which are due to nuclear processes, atomic diffusion, and here you have the processes induced by rotation. So the circulation that we treat with this effective diffusion coefficient, which comes from the fact that there is this very strong horizontal turbulence, which can be treated, which can allow us to treat circulation as a diffusive process for the chemicals, but not for angular momentum. And here you have the shear turbulence in the vertical regions. There are different expressions for the horizontal and vertical turbulence, and actually this is really the weakness of this theory, because when we change one for the other, we have very different results, but we can come back to that later. So here I show you, yesterday somebody was asking what is the actual values of these shear and effective diffusion coefficients. So I included this slide for this. This is for, excuse me, 2 different masses, 2 and 12 solar masses at solar metallicity. And you see that, so you have the shear here with a full line, and you see that except near to the core, the shear mixing dominates the transport of chemicals, both in the 2 and the 12 solar masses. And you can see also that both effects actually increase with increasing stellar mass. Now we can wonder what happens in the case of different metallicity. So you see that for the different coefficients, the values don't change very much. Here you can see the different loops of circulation, of meridional circulation. So there is no significant differences for the different metallicity, but there is still an effect, which is that the low metallicity stars, they are more compact. So the characteristic timescale for the diffusion, which is given by this expression, actually decreases with metallicity, and that leads to more efficient surface enrichment, abundance variation at the surface in the low metallicity stars than in the more metal-rich stars. So as a summary of what we've seen, rotation leads to brighter stars, larger radius, which implies an error on the mass estimate. it also changes the asteroseismic properties of the star. And here is an example for the large separation for radial moles, which are actually 10% different due to the larger radius of the rotating model. And because the rotation-induced mixing brings more fuel to the core, the star with rotation actually lives longer on the main sequence, so the age estimate increases. So this was an example of a 3 solar mass star. What happens for a slightly more massive star, like this 7 solar mass star? So here you see, for the case of moderate rotation, so these are different percentage of the critical rotation velocity, so 10%, 30%, etc. You see that for moderate rotation, these are more the mixing effects, because you bring more fuel within the star, within the core, that you have this increase in luminosity and radius. But in the case of fast rotation, you have also the hydrostatic effects that start to play a role. And here you can see for these kind of models with different masses. So these are models made by Geneva people, where you can see the variation of lifetime for stars of different initial masses, and for different ratio for the initial versus the critical rotation velocity. So here, if you go to very extreme, you can have to very extreme rotation, you can have an increase up to 35% in the mass range considered here. So these are things that are well known, but I would like to show you also some other constraints which are very important, because as I said, we have some uncertainties on this turbulence. And one way of calibrating it is by looking at stars on the main sequence, which are the red stars here. So these are OB-type stars in the galaxy of different classes, and in red you have what can be considered as main sequence stars. And here in dotted you can see the times without rotation, and here with rotation. So you see the effect is relatively modest here in this graph. These are predictions of Ekström and collaborators. And here you have predictions for similar physics by another code by Stern et al. And you see that in these models, the extent of the main sequence is very large, and you have many stars which actually are actually later type stars, which are included in this main sequence width. So that means that in that case, the width of the main sequence, which is predicted, is too large. And it's not due to rotation, it's just due to the fact that there is a stronger overshoot in the models of Brot et al. Compared to Ekström et al. And here you can see an intermediate case of Keffi and Limongi with the code Franek, which also takes into account the same processes. And you see that it's really the overshoot that plays a role here. So we could say it's very difficult to disentangle the effect of overshoot versus the effect of rotation. I will skip this one. But in fact, we have some clues that rotation makes has the strongest impact. Such clues come from different open clusters, so for quite massive open cluster like this one, which has been observed by Gaia. And here you can see the broadening of the main sequence. It's a pretty young cluster. And in these stars, the rotation velocity has been determined through spectroscopy. And you can see that the stars which are broadened, which are on the right side of the main sequence, are actually also the fastest rotators. So this is a strong indication that rotation is more efficient than, is more important than convection in this case. So I will skip this. So for the mixing and its impact not only on the stellar parameters, but also on the chemical abundances, here you have the same models. So these are I will show this one. So in black, you have the model of Geneva, broad models are here, and then you have Keffi and Limongi here. Here in gray, you have some data for galactic stars, and actually these quite low values of C/H are observed only by one group, And all the other groups find larger value of C over H, which are more consistent with the solar value from Groves and collaborators. So probably these abundances are not correct. And when you start with the abundances around the solar abundances, you see that the decrease of this of the carbon to the surface, which is shown here, is well predicted by the models. This is for the main sequence stars here, and here for more evolved stars. And you see that actually these models are pretty in very good agreement with the data. There are many.
Minutes, so you know.
Excuse me.
5 minutes.
Okay.
Just so you know.
Okay. So I will skip that because I would like to spend some time on the thermal mixing. Yes, so the only thing I would say about rotation in low mass star is that when you consider all these processes inside the models of low mass stars, you are very well able to reproduce the surface rotation of the stars. But the difficulty is that you predict internal rotation, which has stronger gradients than what the asteroseismic data tell us. So that means that, and this has been predicted by all kinds of models. So that means that in addition to these transport processes that I mentioned before, other processes play a role and also transport very efficiently angular momentum. And two models have been proposed: internal gravity waves and magnetic instabilities. And I will just show you here the prediction. So this is for the models of one solar mass star with shear and meridional circulation only. And here you have the predictions for internal gravity waves. And here you have the case of the stars computed with magnetic fields. So both transport processes can in principle play a role that has to be investigated. Okay, so I will skip that because I would like to spend some time on thermal mixing. It has been observed for a long time that stars above red giant stars above a certain luminosity, which is the luminosity of the red giant branch, show some abundance variations which are not predicted by the models. This is the main sequence, first red jet, bottom of the red giant branch, and then at the luminosity of the bump, the abundances change. And we have shown for quite some time that this corresponds to the time where the hydrogen burning shell encounters the regions that have been mixed by the convective envelope, and hence the hydrogen burning occurs in a region where there is no gradient of chemical composition. However, the hydrogen burning through the helium-3 produces more atoms more nuclei than it started from, and this leads to an inversion of the mean molecular weight, which we proposed to be related to the thermal instability, because you have an inversion of molecular weight that also destabilizes the temperature stratification in this case, and you have a double diffusive instability. So when we proposed that with Jean-Paul Zahn, we used a very simplistic expression for these salt fingers. We used the Ulrich prescription, and this is what you see here for these three models. So this is the same mass, but you see a different metallicity. And when the stars arrive at the bump, the abundances change. So lithium disappears, carbon isotopic ratio decreases, etc., etc. The problem is that these fingers, instead of plots, are not yet supported by numerical simulation. There is a nice review by Pascal Garot, and now there are some clues that magnetic field might play a role. It's a very interesting topic. It has been attacked by many, many people, but I would like to show you a different angle, actually. If you include thermal mixing in low mass stars, and you include the model predictions into population synthesis models, this is what has been done by Nadège Lagarde, where she predicts for different fields in the galaxy the distribution of C over N. And this is what is shown here in gray, for example. This is for the models with thermal mixing. And all the colors are the C over N abundances which are observed in stars of different open clusters. So when you take into account thermohaline mixing, when you don't take into account thermohaline mixing, you see that the abundances, the observations in the low mass stars are not explained. While when you take into account thermohaline mixing and you put that in your stellar population model, you see that you very well recover the observations. The same is, yeah.
We're very nearly out of time.
Okay. Yeah. Okay. So this is the same, but as a function of metallicity without and with thermohaline mixing. And okay, so I will skip that. I had a very interesting story to tell you about thermohaline mixing, which is related to the Apollo mission, but I will skip that unless you ask me to talk about that, and I will move to my conclusions. The take-home messages for stellar physicists to stellar physicists is that transport counts, it modifies all the stellar predictions. But there are many things we don't know, or we think we don't know, or we think we know, but that depends if we are realistic people, optimistic or pessimistic. And the real difficulty comes from these different scales of different processes, in fact. Leonardo da Vinci said that the details make perfection, and perfection is not a detail, but probably instabilities may lead to perfection, and perfection may be an instability. And the last thing is that for stellar physicists to galactic and extragalactic physicists, the take-home message would be use stellar models with great cautions, because indeed the transport counts and changes all the predictions, but we are far from understanding all these aspects, all these interactions, etc. And if we want to make beautiful galactic archaeology and chemical evolution, we need to hire stellar physicists and people working on these aspects. And with this, I thank you for your attention, and I apologize for being a little bit too long.
All right, thank you, Rick.
Thank you.
Does anybody have questions? I see a couple.
Jorik Vink. I have a question about the massive stars that you showed, the Hesperonychus diagram of Martins and Palacios. Because I think it's the exact opposite. I'm not sure what you were saying, but you say it's too broad, but I think it's not broad enough.
This one, or?
Yeah, those, yeah. So you see lots of stars to the right of the Thames, so that to me suggests you need much more overshooting, or whatever you want to call it, but much more mixing than assumed in the models. Rotation will not solve that. It has to be something else.
Well, here you have I was very fast there. So here you have the luminosity class. And actually,
sorry, the spectral class 5 has nothing to do with whether the star is core hydrogen burning or not.
That's true. But here you would have actually stars which have been inflating already. These ones, the blue ones here, and these blues should not be in this area here.
I see lots of blue points at all the way down to 4.2.
4.2.
Temperatures of log 4.2, 4.1. There's still stars there. So that is very suggestive that these are all still core hydrogen burning. So that the Thames shouldn't be so far to the left, but it should be much further to the right.
But they are class 1.
It doesn't matter what the class is. The spectral class doesn't tell you whether the core is burning hydrogen, helium, or whatever.
Well, not sure.
All right, we have a question from Matteo.
Hi, Corinne. This is Matteo Cantiello speaking. Thanks so much for this great review, and I'm very interested in the effects of thermohaline mixing, and you were talking a little bit about the dependency of thermohaline mixing on metallicity, the work from Nadej, I believe. You had to fly a little bit over those slides, so maybe if you want to go back and tell us a little bit more about what is seen in the data.
These ones. These ones? You
Yeah.
hear me?
So this is the dependency on mass, and I
Yeah.
think it's telling us that the thermal mixing or whatever mixing process is more efficient at low mass, but then we have some dependency also on the metallicity, and that's the part that I'm interested.
Well, I think it's just because here you have actually only low mass stars and in this area, because the more massive ones would be dead.
Yeah, I guess it's just telling us that thermohelium mixing or whatever mixing process is more efficient at low metallicity?
Yes.
Okay, good. Thank you.
Yeah. Definitively, yes.
There's a question from Pascal Garot in the chat. I think it's about this plot asking, are each color points for different stars, and what do the colors represent on this diagram?
Okay, so these are observations of stars in different clusters and also in the field. So all the color points are indeed individual stars, either in the field or in open clusters. And in gray, you have the model prediction for the population synthesis. So this is done with the Besançon galaxy model, which is able to make a snapshot of part of the galaxy that you are observing. And it takes into account IMF, age metallicity relations, so you can predict how the stars would look like if you look into that direction, very precise direction, or in this different field. And this is a very flexible model. So here you can you can predict how many stars you would expect to see in this area, and you see the effect of the models with thermal mixing are included in this simulation here. And you also take into account the age of the star, how much time they take in the different parts of their evolution, and you can predict the distribution of stars here. And you see you see this very large increase of stars in this area, which is just due to the thermal mixing occurring in the low mass, low metallicity stars.
Okay, thanks. There's a follow-up question also from Pascal asking, is it correct to interpret this as saying that there's a huge spread in the mixing, even for stars with the similar masses and similar metallicities?
So it's not really that. It's actually these stars are, if you look at, I don't know if I have one where we could see. So here, for example, you have stars. You see very well the points are aligned. So these are really for open clusters only. And you see here you have the spread. But and I could not include that, but if you were putting the stars along the color magnitude diagram of the clusters, you would see the brighter star would be here and the less bright star would be here. So it's really an evolutionary sequence. You really see the thermal mixing act along the color magnitude diagram. Is that clear?
So just clarification from Daniel Lequin. So you're saying that it's an age dependence. Is that what we're seeing?
Not an age dependence. It's evolutionary phase dependence. So when the star is climbing along the color magnitude diagram, first you have the first redshift that changes the abundances. So you will have these values, for example. And when you move after the bump, actually the star is brighter and the thermal mixing is more efficient. So it's really the evolution of thermal mixing along the color magnitude diagram.
Okay, thanks.
In a cluster, the stars, they all have the same age. What is the slight difference is the slight mass along the color magnitude diagram. The stars changes slightly of masses along the rectilinear branch, but they all have the same age.
Another question from the chat from Amanda Caracas. Sorry, I don't know how to say your name. can you comment on the dependence of thermohaline mixing on the diffusion parameter? Any thoughts on how we can constrain it?
When we found this idea that it could be thermohaline mixing at play, we didn't play with the parameter. We took the one of Ulrich, which was modified by Charbonnel for the equation of state, and we plugged it into the code, and actually we got this beautiful result that we saw here. So we didn't play with it. We got this directly. But in this case, you really have fingers. The blobs are actually elongated. And if you have blobs instead, so you have a lower efficiency, you cannot reproduce the observations. So if you consider this kind of observations, that's a way to actually find the size or the aspect ratio of the blobs of the fingers of the thermohaline instability. And what is also important is that it's only the CNO which is changed. People have looked for the effect of thermohaline mixing on higher elements, because when the RGB actually are brighter, the temperature of the hydrogen burning shell increases, and you could expect, if the thermohaline mixing was going deeper, to change, for example, sodium or even oxygen. And this has never been found. And actually, that was an idea at the beginning, to try to explain the variations of oxygen and sodium in globular cluster red giant stars. People thought that we could have a mixing. So at that time, we didn't think about thermohaline mixing, but we were thinking about a process that could go that deep to this very high temperature of the order of 40 or even 50 million K. But this has never been observed. There has never been oxygen and sodium variation along the tracks in the CMD. And the multiple populations in globular clusters that have different oxygen and sodium abundances must have inherited it from their at birth, actually. So this is a much more complex mechanism of the formation of the globular clusters.
I see. Thank you. Are there other questions from the audience? Yes, we got one here.
Hi, Corinne. This is Jim Fuller. So you mentioned that rotational mixing processes might be able to counteract diffusion and, well, counteract gravitational settling to reproduce the abundances we see in radiative stars. Mm-hmm. What kind of rotational mixing is that? Does that mostly rely on shear instabilities due to differential rotation?
Yes.
Or is it the meridional circulation itself?
No, it's the shear, actually. It's the original work was made by Suzanne Talon and working with Olivier Richard. Where is it? And actually, well, I don't know where it is, but and they actually, so what they did is that Olivier Richard computed determined the parameterization to counteract atomic diffusion in order to explain what we see in globular clusters, this variation. And so he had an amplitude and the depth for the mixing, for this turbulence. And what Suzanne did in another code was actually to compute the amplitude of the turbulence that was coming from the rotation model Al-Hazan. And it was mostly shear turbulence that was coming from this work.
Okay, so
if dominating.
If I can ask a follow-up question, we know from helioseismology that the sun's core rotates mostly rigidly, and from astroseismology that there's less shear than hydrodynamic-only models would predict. So would that reduce the amount of mixing that we should expect, and does that challenge these results?
So the thing is that in the sun, indeed, we have less transport due to shear because of other transport processes. In the case of these stars, which are slightly hotter than the sun, there is the depth of the convective envelope is much thinner, and the fact is that we don't know in these stars. So for the solar metallicity, that means stars with masses higher than 1.3 solar masses. And in 1.3 solar masses, we don't know if the rotation is rigid or not. And if we consider internal gravity waves as a solution to the transport of angular momentum in the sun, the fact is that these internal gravity waves, we expect them to be efficient only in stars which have masses below 1.2 solar masses, because they have to be excited by the convective envelope that has to be deep enough. And there is a tracer of these, the occurrence of the internal gravity waves, which is, from my point of view, which is the lithium dip. So when you look at lithium as a function of effective temperature in open clusters like the Hyades, you see that in cool stars, the lithium is depleted, then there is kind of a plateau. And at a temperature above 6,700, you have a dip of lithium. And if you have internal gravity waves, you have a very specific way to explain that, is that at these depths, the convective envelope becomes deep enough, so in the cooler stars, to have internal gravity waves starting to play a role and transporting angular momentum beyond meridional circulation and turbulence, which could explain the sun and low mass stars, so the rigid rotation, while in stars which are hotter, gravity waves are not excited, and so you have no additional transport process, and then you would have non-rigid rotation. Now, if you consider magnetic instabilities, there is no reason why there should be an effect depending on the depth of the convective envelope or on the effective temperature of the star. And from my point of view, this lithium dip and this kind of explanation is in favor of the internal gravity waves transporting angular momentum in cool stars instead of magnetic instabilities.
Okay, thanks. I just wanted to comment, there's some nice astroseismic results from Timothy Van Rieth, who's here, which shows that gamma Doradus pulsators, the core rotates at almost the same rate as the surface. So we do have some nice constraints that there's not very much shear in those stars.
Okay, well, one problem after the other. But, and then I would say, okay, but let's try the internal gravity waves from the core.
Other questions from the audience? Matteo has a quick question back, and then this will be the last one.
Matteo Cantiello, I don't want this to go too long, but I'm still very curious about what thermohaline mixing and diapole emission have to do with each other. I know you had a story for us.
Well, I think I need more than 1 minute, but I can try. So it depends if you want me to do it after next talk or as you want.
I think in the interest of time, if that's all right, we might need to convert over to the next speaker. But I agree with Matteo that I'm kind of curious to know about this, so maybe you can tell us another time.
Okay.
So with that, let's thank the speaker again.
Thank you.